Hello, George Romanic here. Today I will show you the most complicated equations on YouTube and beyond. Some of you might be suspicious, thinking this sounds like a clickbait, and you are partially right. You are partially right because these equations that I will show you are Navier-Stokes equations in atmospheric sciences. They cannot be solved, and if you find me another set of equations that cannot be solved, then they are equally difficult. If I give you an option to be hit by airplane or be hit by train, in both cases you will die. I ask you which of these two is worse. Answer is equally worse. They are equally fatal. Therefore, these equations that cannot be solved analytically are equally fatal as some other equations that cannot be solved analytically also. Now, without any further ado, let's see those unsolvable equations. Ladies and gentlemen, boys and girls, what you see in front of your eyes are, in my not so humble opinion, the most complicated equations on YouTube. These are Navier-Stokes equations in atmospheric sciences. So if you study atmospheric sciences, you see what kind of beasts you need to tame. You see how smart at the end of the day you will become if you can understand what is going on in this mess. And I will try to explain to you in simple words what these equations mean and each term in these equations. First terms on the left are local derivatives of three velocity components u, v and w. U and v are two horizontal components. U is positive towards the east, v is positive towards the north, and w, which is vertical velocity, is positive upwards. These terms tell us how velocity changes with time. T is time at a fixed point in space. So these are basically prognostic terms. They give us forecast. Then the black terms, three terms in each of the three momentum equations, are the so-called advection. First two are horizontal advection and this is vertical. These three are vertical advection. These terms are difficult to comprehend in our brains. To try to help you visualize these terms, I will actually write advection of temperature. That would be, for example, U delta T delta X. I see my marker is dying. Now, this is still difficult to comprehend in our brains, but at least what we can imagine here is the following. U component of wind is advecting temperature field across the X direction. So, if you have here, let's say, T1, temperature T1, here you have temperature T2, and this is my X direction, then, and the wind is blowing like this, then the wind is advecting temperature field. But the situation is more complicated than this simple explanation, because as the wind is advecting temperature, temperature is changing pressure and then pressure changes wind. So wind advecting temperature changes itself. This was very simplified explanation. The same reasoning holds for the advection of wind components, but we are saying that in this case, wind is advecting itself. V component is advecting U component. W component is advecting in the vertical direction U component and so on. So don't try to think too much about it. These are nonlinear terms, and they are one of the reasons why nobody can solve analytically Navier-Stokes equations. Function is multiplying its derivative, and that's nasty in mathematics. Another nasty terms are these that I put in red because they are so nasty, and that's curvature terms or metric terms, and they are consequence of our beautiful planet Earth being a sphere-like object. In atmospheric sciences, we assume Earth is perfect sphere, although it is not 100% perfect sphere. Here, phi is latitude, r is radius of the Earth, and again, u, v, and w are velocity components. I explained in one of my previous videos that curvature terms arise because if we have planet Earth, and let's say this is k vector, unit vector k pointing up, look, as parcel of air moves around, the orientation of this vector changes. As it moves in the direction of latitude, this vector again changes. If this is I unit vector, and that is positive eastward, then look, as we go around the sphere, the orientation of this vector changes. The same is for j vector, that is positive north. As the air is moving in the latitudinal direction, the orientation changes. And these terms explain these changes. The next three terms are pressure gradient force, and they are good boys. Pressure gradient force is the only force in these equations that can initiate motion of air, or for that matter, water or any other fluid explained by these equations. So everything that happens is initiated by these terms, pressure gradient force, where ρ is density of air and P is pressure. Delta P, delta X is pressure gradient in the X direction. This would be pressure gradient in the Y direction and pressure gradient in the vertical direction. G is also simple force, that's gravity. G is gravitational acceleration, which is gravitational force per unit mass. And then these pink terms are also not so easy to comprehend. These are viscous forces. Air is fluid, and we said viscous forces can be imagined if we have two layers of fluid, like this. As this one is moving in this direction, it tends to drag the layer underneath with it. Or, if this one has smaller velocity, you could also say this layer is slowing down the layer that is moving faster. And this relationship between layers is described by viscous forces. So these are virtual layers. There are really no layers in the fluid like this, but we impose this approximation to quantify viscous forces. Viscous forces can also be visualized as following. You go on a train to some long distance trip, and you put your hand through the window, and your girlfriend is right here, and she is sad that you are leaving. She holds your hand, but as the train moves, no matter how strong your hold is, you will be separated. The same is here. There are molecular forces acting between these two imaginary layers, and they are holding each other, just like boyfriend and girlfriend holding their hands. But if the pressure gradient force that is, or advection, that is moving these layers is stronger than the molecular forces over here, this layer will tend to move above this layer and so on. In other words, viscous forces will not be able to oppose the overall movement of these, the relative movement of these layers. Last terms here are Coriolis forces, or Coriolis force, just different components in these three momentum equations. Some of you might ask, why didn't I put 2 in front of everything? That's more common. Am I a beacon? The reason is no, I'm not a beacon. Usually we give this term 2 omega sine phi abbreviation f, and we call it Coriolis parameter. This 2 omega cosine phi then becomes f prime, also has its abbreviation, and phi is latitude, as I said, and omega is angular velocity of our beautiful planet. Terms that are really important in atmospheric sciences and oceanography are these terms that are proportional to sine phi and horizontal velocity component. So in atmospheric sciences, we generally neglect this term, W cosine phi, as well as this term here, U2 omega cosine phi. So in practice, we usually end up only with these two terms. Why do we neglect these terms? You can watch my video on traditional approximation in atmospheric sciences. Namely, they are much smaller than the components of the Coriolis force in the horizontal direction. Coriolis force is extremely important at large scales. In northern hemisphere, it deviates motion to the right, and in southern hemisphere to the left. Coriolis force is a parent force, fictitious force, which means it cannot do any work. If there is no motion, there is no Coriolis force. If there is motion, Coriolis force will only change direction, never intensity. Let's say you have wind vector like this, and we are in northern hemisphere. Coriolis force will act to the right of this motion, but the length of this arrow will stay unchanged. So Coriolis force will tend to deviate this motion to the right, as I indicated here, changing the direction of this vector, but never intensity. Perhaps pause video for a few seconds and admire the complexity of Navier-Stokes equations in atmospheric sciences. Do you think you can solve this beast with 3 heads? Do you think you're smart enough to do that? Many tried, nobody managed. I don't know if you are smart enough to do it, but I can tell you a few other things about this system. First of all, this system is mathematically not closed, that I showed you these 3 equations. There are 5 unknowns, 3 equations. But that's trivial problem because we can add equation of state for ideal gas, we can add mass continuity equation, and also a first principle of thermodynamics. We close the system, but it doesn't help. We still cannot solve it. We cannot solve it because equations are complicated in layman terms. In professional terms, we would say they are nonlinear, non-homogeneous partial differential equations. Nevertheless, these are the equations that we use in weather forecasting. I always tell my students, if you forget everything I tell you, at least remember that weather forecast is calculated. It's not some people looking at some other people and discussing how weather could be tomorrow. To a certain degree, that also happens, but in principle, weather forecast is calculated using these equations in one form or another. Now I just told you equations cannot be solved. Then how do we calculate anything? They cannot be solved analytically, but we can solve them numerically. And that is a huge research field in atmospheric sciences and oceanography. Numerically means derivatives are approximated as finite differences. How to do these approximations? What is the best approach? What are the errors that we introduce? I will discuss that in some of the future videos. Inevitably, we introduce errors because we move from partial derivatives or derivatives, which are infinitesimal concepts, differences, to finite differences. And there are many other things that introduce errors. That is one of them. To conclude, now, if you stumbled upon by some chance on this channel and you listen until now, keep in mind these are the equations that tell you what the weather will be like tomorrow at your place. Thank you for watching. Until next video, goodbye.